Hi everyone, welcome to the uh, machine learning using Python. We are working on the classification problem. Last module 4 we had done the part of linear regression. Obviously classification will involve the logistic regression without saying that because done a great job in the previous session, although it was a longer one, but it was one of the uh, great ones with all good explanation. So we look forward to having him machine learning using Python. We'd like to hear from him. Thank you very much, Jamit. Please take over from here. Welcome.
So thanks, sir, for the intro, and hi everyone. This is machine learning using Python, and today we'll be going. Today we'll be learning about the classification problems. Specifically, we'll be focusing on binary logistic regression. But first, let's just discuss the goals for today's session. First is to understand the classification
Just a
problems.
minute. Just a minute.
Yes.
You are muted for a few seconds, so we didn't hear anything about the introduction. After you are saying that this is machine learning using Python,
I
can you
don't
just
know.
repeat what you said?
Just a second, let me just switch over to different data so that this disconnection doesn't happen. Just a second. Hello, is my voice clear? Hello.
Jamit, I cannot hear you. What's going on?
Yeah. Is my voice clear right now?
Yes, it is clear. Yeah, go ahead.
Yeah. Okay. So, hi everyone. This is session 7.1 for module 5, which is on machine learning using Python, the classification problems. Today, in this session, we'll be focusing more on the binary logistic regression.
Good.
So, the learning goals for today's session are to understand the concept of classification problems and the application across different sectors. Then, learning the um, learning to build the logistic regression model called logit function by the stats models library and the scikit-learn APIs. Then we'll be splitting the dataset into the training and validation sets as we have done in the past session as well. Then we'll be discussing about confusion metrics, how we'll be applying the confusion metrics in our case, and also discuss the ROC curve, or also called as receiver operating characteristics curve, and area under the curve for AUC. Then discuss some of the model diagnostics, the significant features that will impact the model and give us the best results, and also find out the optimal cutoff that can be used for our case. So let's get started. First, I would like to walk you through some of the basic stuff. So we, uh, we, we are right now in the time where AI is the buzzword. So what is AI? AI is the ability for the computer to think and act like humans in a very simple and a layman definition.
Jamit, you are cut off for almost the whole part of the slide in the end. Anyway, continue, but keep continuity, okay?
Yeah. It involves training a model. So when we try to teach a model to learn a specific task with the help of data sets uh, consisting of consisting of different things depending on the case we are building. Uh, we can term it machine learning, where we teach the model to learn a task and then make the model do the work in real world scenario. Then comes deep learning, which gets more deeper into the case and performs complex tasks or gives more deeper and detailed insights. So you can see by the Venn diagram that what is the relation between the artificial intelligence, machine learning, and deep learning. So as we are discussing on the machine learning, we'll be discussing few of the machine learning categories and go through them. So machine learning category has been divided into supervised, unsupervised, and reinforced. The supervised learning, we already know the problem, and we are making the model learn to get to the results that we want, and make the necessary changes in the model so that model improves and learns the task. In supervised learning, we do not know the output, but we let the machine learn the patterns and discover the patterns and learn the patterns. In the reinforced learning, the machine learns based on the reward-based approach. If the machine does something that we want, we reward it and stuff. So supervised learning has this subcategory of classification and regression. We use a regression when we are trying to predict a continuous value. We use classification when we when we are trying to predict a class of which the a particular uh, a record or data point belongs to. So this classification is divided into binary and multi-class. In binary classification, the classification is divided into two parts, whether it belongs or does not belongs to. In a simple example, we can take an example of a picture. If the picture contains a dog or not, so that becomes a binary classification. In a continue in a very in a statistical approach, or let's say not statistical, but in a data-based approach where numbers are involved, then we can say that certain threshold it belongs to this class, and after a certain threshold it belongs to the another class from the two of them. So this is what the binary logistic regression will be discussing about in the binary classification. So before jumping onto that topic, let's just take a few examples just in order to get clear about the classification. So a bank trying to know the customer, which are the risky customers and which are the customers at low risk or high risk. Then comes the e-commerce platform trying to predict whether a customer is likely to stop using their product or continue using their product. Then health service providers may classify a patient based on diagnostic results such as positive or negative for various kinds of test results, medical test results. The HR department trying to predict if an applicant would accept an offer or not, or predicting an outcome of a sporting event, or the sentiment analysis of a customer on whether it's a positive, negative, neutral, or sarcastic remark. Then, based on the image of a plant, one can predict if the element of the plant is infected with a specific disease or not. So I hope the classification is clear, and more specifically what the binary classification means. So some of the techniques that we use for classification are logistic regression, classification trees or decision trees, discriminant analysis, neural networks, and support vector machines. In today's session, we'll be discussing about logistic regression. What is a logistic regression? It's a supervised machine learning algorithm that accomplishes binary classification task by predicting the probability of an outcome, event, or observation. Now, that outcome can be labeled as a yes, no, true, false, or 0 or 1. And that's how basically most of the binary tasks are classified, and depending on the labels, their meanings are it can be assigned. So, first of all, binary logistic regression is a misnomer. The the logistic refers to the logic or the log odd functions. So let's say that we are dealing with probabilities. So if there is a probability of y equals to 1, meaning y belonging to a certain class, then that will be provided by probability of y equals to 1 equals to e raised to z divided by 1 plus e raised to z, where z is not z is nothing but the linear function, which is beta 0 plus beta 1 x1 until beta m xm for m number of inputs. Beta 0 is nothing but the intercept itself for telling us the value of the effect if all the other features are 0. So logistic regression has an S-shaped curve, also known as a sigmoid curve. As you can see, this is the example of a sigmoid curve, sigmoid function in the graph below. The the log of probability of y equals to 1 to 1 minus probability of y equals to 1 equals to z, which gives us the linear function. The left hand side gives us the log natural of odds, or also known as logit function, for which the logistic regression is the name. And the right hand side is the linear function, which are generally called generalized linear models, or GLM. The error, like in linear regression function, they might not error or residuals like in linear regression functions, they might not follow the normal distribution. And there exists a transformation function of the outcome variable that takes a linear functional form. So as said about the sigmoid function having an S curve. So if we are trying to predict the heart disease based on age function, this might be the curve. As the age increases, the chance of having a heart disease increases too. So in this binary logistic regression session, we'll be taking the example of a German credit rating dataset, which is provided by UC Irvine ML Lab, and we'll be predicting whether the credit is good credit or bad credit. So the dataset itself has a lot of categorical values, or is categorically divided. So you can see that if there is checking account. That checking account is a categorically divided into four different parts for from A11 to A14, having A11 belonging to less than zero Deutsch mark, to A14 having no checking account, or A13 saying the balance having greater than or equal to 200 Deutsch mark. Then comes the credit history. Uh, what from A30 to A34, it shows different possibilities of the credit history, having no credit history, to A34 being critical account or other credits existing, not which does not include the this very bank. So this is the whole data set from amount, savings account, present employment, and interest rate, personal status, then residing at a place since when, then comes the age, the insurance plan, sorry, it's the installment plans, then checkings account we have already discussed about the different kinds of accounts. Then comes the job and the various categories involved with the job, and in the end the status says that 0 for good credit and 1 for bad credit. Remember that for good credit we are labeling it as 0, and for bad credit we are labeling it as 1, as it's easy to take 1 for good credit and 0 for bad credit. So you can see that there are many categorical columns as also mentioned while explaining the data set over here. And we also took the same example as in the slide, and for the checkings account for from A11 to A14. And when we say when we check the information regarding the data set that we are using, you can see that there are total 14 columns, 1,000 entries, out of which there are 7 columns which takes object data object data type as values. The other ones are other 7 are taking integer data type as a value. So uh, the you can see that from the data set, the objective types are the ones that are categorical values. So those are the reason that these are the checkings account that we saw over here is an objective type and not a numerical type. So to find the number of good credits and bad credits, as you can see, as you know that we had a last column as a status, and in status there were 0 and 1 as a good credit and bad credit respectively. So to count the values of good credits and bad credits in the entire data set, we use the value counts function, or sorry, method, and we have 700 total good credits and 300 as bad credits. So we'll be creating this logistic regression model. So in order to get the logistic regression model, we'll have to create the X features or the independent variables. So you can see that we are, if you look at the right hand side of the screen, there is a snapshot of X features. So we are creating X features from the credit DF in terms of list, and then we are removing the status column from them, because that status column will become our dependent variable. So that is the reason we are removing the column. So after removing the column, you can see that this is the list of all the columns that we have, from checkings account, duration, credit history, all the way to the job. So as you remember that we have talked about categorical values and them being inferred as object data type from here. So checkings account is one of the example. A lot of them had categorical values. 7 total columns had categorical values. So we are going to convert them in through one-hot encoding and use dummy variables. So let's just understand what is a one-hot encoding first. You can see in the image that we have sunny, rain, and wind. So for sunny, the value becomes 1 and 0 for other two. The same goes for rain and wind. When rains, it has the value 1, and the wind has value 1 for itself when it's windy. Now this is a simple one-hot encoding, but when we use it as dummy variables, there is a problem. If I want to predict that whether the weather is sunny, I can predict it by seeing that the rain and wind values are 0. The same goes for rain and wind as well. If I want to predict rain, then I can infer it from the sunny and the wind values of being 0 that the value is rain. So this is something called as a multicollinearity and linear dependence. So we don't want the model to infer from these kind of values, but rather from the data. So that is the reason that when we use one-hot encoding and use the dummy variable and convert them into dummy variables, we remove one of them. So like in this case, if we are one-hot encoding, let's say we drop sunny as the column. So that column will be dropped, but it won't be uh, deleted or something, but it won't be simply used. So sunny can be used, the dropped column can be used for the reference purpose, but we will not make any kind of inference using that. So this is what the whole dummy variable type means. The first is a multicollinearity, where when all n dummy variables are included, they are linearly dependent. This means that the sum of all the dummy variables equals 1 for any given observation. This leads to perfect multicollinearity, where one dummy variable can be exactly predicted from the others. Then comes the linear dependence, including all n dummy variables introduces a redundancy because one category can be expressed as a combination of others. If you, for example, if you have a categorical variable with 3 categories A, B, and C, you only need 2 dummy variables to represent them, which is dummy 1 if A, 0 otherwise, and 1 if B, and 0 otherwise. The third category C can be inferred if dummy 1 and dummy 2, both of them are 0. It's the same kind of expression that we did for or discussed over here. So we'll make the dummy variables. So using the pandas get dummies method, and using the X features from the credit DF that we have used, and drop first means that we are dropping the column. So dropping the first column. So it goes for all the categorical values. So you can see that checking accounts in the list, you can see the list that we get after creating the encoded credit DF or one hot encoded credit DF, if you want to be really descriptive. So when we print the list of the columns that is present in the encoded DF or encoded credit DF, you can see that checkings account used to be from A11 to A14, but because of our argument value true for drop first, it dropped the checkings account A11. That same thing will be happening for all the categorical values, so that inference or direct inference cannot be made. So as I said that the A11 is dropped. If we print the encoded credit DF, you can see that there is no checking account A11. Now we'll be using the stats model API to make our model, and we'll be using the logit model for building the logistic regression model. So what we have to predict was the dependent variable, so which was status, that we removed from the X features, and X features had all the encoded credit DF or all the values with the uh, one hot encoded data frame. And we are using stat models add constant in order to add the intercepts value an additional column as constant, and all the values within that will be 1. So now we'll be using the scikit-learn's model selection to split the data set that we have into train and test. So we have used it before also. So X test, Y test, X train, and Y train. And sorry, not according to the order. X train, X test, Y train, Y test for the XY values, as well as the test size is 0.3. So 70% of the data set will be used for training purpose, and the random state value we are giving is 42. The the so as I said that we'll be using the logit method from the stats model API module, stats model library, and API module. So when we fit the data that we are using with the model, we get the output of optimization terminated successfully. Current function value is 0.488. Now these values will be saved into our logit model variable that we have created, and which will be used for further use. So when we print the summary of the logit model that we have created using the logit method and fit the model, this is the whole summary that we get. You can see the number of iterations, then scale, then number of observations, the different coefficient values for all the categorical values that we created, and the standard error and stuff. So to diagnose the model, we we have three. There are usually three methods that are usually considered. One of them is a Waltz test, used to test the significance of individual predictors, used to know which are the most influential features from the dataset, and give us the list of it. Then comes the likelihood ratio test, used to compare the fit of nested models, determining if additional predictors improve the model. Then comes a pseudo R square, provides an indication of the model's overall goodness of fit, analogous to R square in linear regression, but adapted for logistic regression and other models where traditional R square is not applicable. So first, we can see that in this summary, there is this coefficient standard error z and the probability value greater than z. So you can also see that there are total 8 columns that are highlighted by a red underline. So why do we do that? We'll come back to it. For Waltz test, as said, that it tells us the most significant features that are present in the data set. So for that, we'll be building a function called get significant variables. And what it will take as a parameter is the model that we have created. So we'll be using the probability values of the models that is present, and from the from that we'll be also naming a probability value df as variables, a new column for the index, and also we'll be creating the columns p vals and vars. What it will do is it will return a list of all the column names which has the probability value of smaller than or equal to 0.05 in the variable section. So significant vars is the variable that we create to get to use and store the values of the significant variables in the data set from the logic model that we have created. So when we use it and print the results, these are the 8 column names that turns out for satisfying a condition of probability values smaller than 0.05. So these are the columns that have the most significant impact on the model. So you can have duration, amount, interest rate.
Zenith, we are missing you.
Sorry. Hello. Just a second. Sir, are you there? Sir, are you there? So, hello?
Jamie, a lot of record was missing. I did not hear you for a few minutes almost.
No, no, I was, uh, I actually stopped when you last time stopped me. So after that, I have not spoken. Hello? I'm not able to hear you, sir. Shall I continue or hello? Sorry, we are facing some issues and we'll be continuing. We'll just keep a timestamp for the missing time so that it can be skipped directly. So I hope you are able to listen or the record is being recorded as the for the intended result. So we are at showing that the Waltz test give us the most significant values which impact the model's performance and gives us the best result. So these are the 8 underlined columns that get the and that were suggested by the Waltz test. So as we have we have used the get significant variables and then got us the result for these 8 columns. We'll be building the logistic, logistic regression model using those columns alone. So for the current functions value, when we basically fit the model, the current function value of 0.5 and 1. The last one we get 0.488 and the number of 6 iterations. So to summarize the final logic model that we have created, this is the summary that it provides. Now you can see that there are negative and positive values in the coefficients of the column names. So these negative signs means that if they increase, it indicates that the probability of being a bad credit decreases, while if the ones that have the positive sign, they if those values increase, it means that the probability of being a bad credit increases. So some additional observations from the model's outputs: the log of odds ratio of or the probability of being a bad credit increases as the duration, amount, interest rate increases. And so for example, 1 unit of 0.019 of a duration increase changes in the log of odds of ratio. Then the second point says that the probability of being a bad credit decreases as age increases. So this means that older people tend to pay back their credits on time compared to younger people. Now predicting on test data using the final model on test data using the significant variables to predict using the predict method and using a new data frame to compare for the accuracy measures. So we'll be using the Y prediction DF using the actual and predicted values by the model. And when we print the random 10 sample for the random state of 42 that we have used, we are getting these actual and the predicted values. So you can see that when we have used the significant variables, we have used the cutoff probability of 0.05. And in this, you can see that there can be some records that were poorly predicted by the model. So this is happening because we have used the cutoff probability of 0.5. Sorry for the pause, as there was some network issue, so that is the reason. So we were on the cutoff probability. Now these bad results are the results because of the cutoff probability that we have used, which was of probability values of greater than 0.05, not 0.5, 0.05. Just a second. So, so you, so, so for the probability values of greater than 0.05, these are the bad credits, and the rest of them are good credits. So what we'll do is we'll take the actual predicted values and show them as they are being as a snapshot has been used to present what we are trying to do. So what it's basically doing is the actual and predicted values, like you can see over here. We are using the model's prediction, what it has predicted. So we will do it with the y-pred df or y-prediction df that we have used, and we use the predicted probability and map the function using the and define a lambda function within it for the values 1, and if the values are greater than 0.5, then if the just a second. Yeah, so every record more than 0.5 will be termed as bad credit. Sorry for this. So it's true for the probability values that the cutoff is 0.5 and not 0.05. Sorry for the confusion. So probability values greater than 0.5 are bad credits, and rest of them are good credits. So we'll be creating a data frame which consists of only which adds a column of predicted, which consists of all the predicted values greater of the predicted values of 0.5 greater than the records value as 1 and others as 0. So you can see that the value for observation 557, which is the first observation, we get 0.08, which is low, whereas it is actually a bad credit. And then in observation 332, we have the probability value as 0.8, which is a bad credit, and it is predicted as a bad credit. So there is some inconsistency within the model. It is because of the the cutoff value that we have provided is 0.5. So in order to see which are the ones that the model is where is the model making mistakes, like you can see that 557, the first one, which is a bad credit but predicted as a good credit. So these are the kind of values which can be and which can be defined as a with the help of or which can be more correctly understood with the help of confusion matrix. now if so confusion matrix is nothing but uh, the matrix which helps us understand the true positive values, true negative values, and false negative, the values that are falsely predicted as negative, and the false positive values which are falsely predicted as positive values. So we'll be creating this confusion matrix for our YPRED-DF using the matplotlib pyplot library and matplotlib library and pyplot module and cbond library. So we'll be doing this with the help of a custom function called drawCM for confusion matrix, then use the matrix.confusion matrix for creating the confusion matrix through matplotlib, scikit-learn, and use the heat map to create the confusion matrix and as well as the label them. So you can see that using this we are creating the confusion matrix, and in the row of bad credit for the true label you can see that there are total 91 values, and out of them 61 are predicted as false and falsely predicted. So it for the cutoff probability of 0.5. Now, the false positive is also called as a type 1 error, and the false negative is called as type 2 error. So, for measuring these kind of accuracies of the model, we will be measuring them through sensitivity, specificity, precision, F-score. So first, the sensitivity, which is nothing but the true positive or the number of true positive by true positive plus false negatives. The same abbreviations goes for all the values. In specificity, the true negative divided by true negative plus FP. For precision, TP plus TP plus TP divided by TP plus FP. And then in the end, the F score, it's 2 into recall. Recall is nothing but the sensitivity or the first formula into precision, which is the third formula, divided by recall plus precision values. So when we do this using the classification report for our Y prediction DF that we have used for the actual and the predicted values, these are the scores that we get. We get the precision call for good credit of 0 and bad credit of 1. So precision, recall, and F1 score, we have so these are the values for the precision, recall, and F1. So precision for bad credit for class 1 indicates how many predicted as bad credit instances were actually the bad credit, and recall for bad credit indicates how many of the actual bad credit instances were correctly predicted. And the F1 score balances precision and recall, providing a single metric to evaluate the performance on predicting bad credit. So according to the cutoff probability that we have used, which is 0.5, our model is not performing well. So we'll be trying to set or use our most optimal cutoff probability. Before that, we'll be using a histogram plot, a distribution plot, in order to understand the good and bad credit in the prediction DF that we have used. And you can see that there is a certain kind of overlap for the bad and good credit. larger the overlap between the predicted probabilities for different classes, higher will be the misclassifications as we have seen. So for this, we'll be using the receiver operating characteristic and under area under the curve or AUC. Now, receiver operating characteristics, they are the graphs for the true positive rate and the false positive rate on y and x axis, and they plot the graph for those values. Then area under the curve quantifies the overall performance of the model with a high AUC indicating better discrimination ability between positive and negative classes. In essence, use ROC and AUC provide insights into how well a classifier can distinguish between different classes, making them essential tools for evaluating and comparing classification models. So we'll do that. We'll create the ROC and AOC curve using the by building a custom function of draw ROC. Then we'll be using the scikit-learn matrix to use the ROC curve method, and in the end calculating the ROC AOC score. So you can see that this is somewhat the ROC curve looks, not somewhat, this is how the ROC curve looks like, and the diagonal dashed line that you see, it is for the 0.5 cutoff probability that we have used, and it is calculated as it forms a right triangle at the bottom. So that is the reason it's a 0.5. Then so AOC of at least 0.7 is required for practical applications of the model. AOC greater than 9 implies an outstanding model. Caution should be exercised while selecting models based on AOC, especially when the data is imbalanced. Where the data of positive and negative, whether positive or the negative are way too much out of the proportion, they can be called as imbalanced data sets. So AOC can be very high, but either sensitivity or specificity values may be poor. So AOC sorry, AOC score, the matrix dot the ROC AOC score will be predicted using the Y prediction DF for the actual and the predicted probabilities and round them for the AOC score. So we are using the ROC AOC and we'll be using the optimal cutoff. We are trying to find the optimal cutoff. We cannot just randomly find, though we can find it, but it can be very time consuming. So in order to find the optimal cutoff, there are two methods called Ewden's index and cost-based approach. So the Ewden's index, the variable threshold, captures the corresponding cutoff probabilities. We can take difference of TPR and FPR and then sort the values in descending order. Now, what does simply the Ewden's index does? As you can see in its formula, that it maximizes the value of sensitivity and specificity in order to get the most the highest number possible in the from 0 to 1. So as closer to 1, the model is going to be at the best class optimal classification cutoff. So we will be using the TPR FPR for choosing the data frame and also for applying this Ewden's index formula. And in the end, we'll be using the displaying the displaying the values in descending order. So for the Ewden's index, and after using the Ewden's index, and we get the probability of 0.22, as you can see the thresholds. So 0.22 is our optimal cutoff. So we'll be using the using the confusion matrix in order to understand. So you can see that out of last time it was 91 records that were predicted poor. Out of 91 records, there were 61 records which were predicted poorly, but in this there are 77 records that are predicted correctly and 14 poorly or misclassified. And also you can see that the increase in the F1 score compared to the last one. So the F1 score that we had before was 0.42 for the cutoff probability of 0.5. Now using the 0.22 as the cutoff probability, we get the F1 score of 0.61. Next is the optimal cutoff approach of cost-based approach. Now, as Ewden's index maximizes the values of true positive rate and false positive rate, the cost-based approach actually tries to minimize the difference in the decisions and gives us the best cutoff probability. As the cost of the false positive and the false negative is not seen, what we mean by that is imagine that you are trying to you are having a medical test. If it's a false negative, there is a let's say $100 is the amount, and if it's a false positive reading for the test or the result of the test, it's $200. So you can see that different false negatives and the false positives have a different cost associated with them. So cost-based approach minimizes these costs and give us the cutoff. So we use the so the total cost can be false negative into C1 plus false positive into C2 for the cost associated with the false negative and false positive values. So we'll be getting we will be defining a custom function for get total cost for our cutoff values and applying the formula that we have seen over here in this, using the confusion matrices actual and predicted value of 1 and 0, or bad credit and good credit. Then using the cost df for the probability and the cost, and in the end these are the values that we get. So let us assume that the false negative are 5 times costlier than the false positives. Deciding the cost will require domain knowledge, so we can calculate the penalty of cost of each probability values between 0.1 and 0.5 with increment values of 0.01. So and then sort them in ascending order to find the optimal cutoff first. So using this iterating through using the for loop and for the values in the Y prediction DF that we have been using and the cost DF that we have made. When we use the cost DF and sort the values for the cost according to the cost and in the ascending order, the first 5 values that we get are these for a probability of 0.14 and the cost of 150. So the lowest cost is achieved at a top of 1.14 if false negatives are assumed to be 5 times costlier than false positives. So predicting the values at the cutoff of 0.14, you can see that from this confusion matrix, it is of 77 bad credits for predicting the bad credit. Sorry, we are at 85, 85 from out of 91. So we are able to predict the bad credits, uh, or there is an improvement in the model due to the change in the cutoff of and keeping it at 0.14. So just to summarize the whole summary for the from the binary logistic regression to the uh, for the German credit rating system to the cost-based approach that we have used. So we imported the necessary libraries, pandas and NumPy, read the dataset and gave it the name of credit DF. This is the whole summary for it, and we had 7 categorical values. You can see these are the categorical values that we had, and these are the number of good credits and the bad credits. So for giving the model, we created the X features and the Y features. In X features, we included all the columns and then later removed the status and made it the dependent variable. So, and also we encoded the categorical values into one hot, encoded them and made them as created dummy variables for them. So you can see the dummy variables that were created for these values. And as you can see that we create dummy variables for n-1 values. So if there are 3, we create, if there are 4 total from A11 to A14, we create dummy variables for n-1 columns. Then we checked, and you can see that we have no checking account A11. We directly A12 to A14. Then we use we created the intercept values using the add constant, splitted the dataset into training and testing set, fit the model, use the logic model from the stats model, fit the model, and this is the summary that we get from the model that we have. Now we use the Waltz test in order to get the most significant variables for which we defined this function, and this function returned us these values. These were the columns that made the most significant impact. So we created another model with only these values and the summary. Now it was time to predict the values based on the model that we have made. So we made a Y prediction DF, and you can see that we predicted these values. The predictions were not as per the want as we needed, because we made the cutoff probability as 0.5. So in order to get the cutoff, to know the values, which ones were created as 0 and which ones were created as 1, we made this this sample we print this sample, and these are the values that were predicted by the model. The actual value was 1, but it was predicted as 0. So these kind of inconsistencies were present in the model. So in order to get a deeper insight into how many records were predicted as false and false positives and false negatives, we created a confusion matrix. This is the code for it. We use the matplotlib and cbon, plotted the graph for the confusion matrix, and this is the confusion matrix that we get for the values. So you can see that there are total 91 values as bad credits, but 61 of them were predicted as good credit. So in order to get, and also the classification report using the scikit-learn matrix, this is the F1 score that we got for predicting good bad credits, which is 0.42, which is very low. And also we used a distribution plot. The larger the sorry, the larger the overlap between the bad credits and good credits, more misclassification is bound to happen by the model. So you can see there is a good amount of overlap. So we use the ROC curve in order to know the true positive rate and false positive rate for X and Y, for Y and X axis. So you can see this is the ROC curve that we got. This is the diagonal is the 0.5 cutoff probability, and the AUC score that we get is 0.78. You can see over here, or also at the bottom of the curve. Now we want to see the cutoff probability, or choose the optimal cutoff probability. We used a Udens index and Udens index and cost-based approach. So Udens index gave us the false positive using the true positive rate and the false positive rate. This was the probability given by Udens index as 0.22. So we used that probability, and using that there was an improvement, and we can see that with the confusion matrices different values, and 77 good bad credits were predicted as bad by the model. Now for the classification report, our F1 score has also increased from 0.41 something to 0.61. In the cost-based approach, we defined this custom function, applied the the formula for the cost-based approach with the false negative and false positive values, and the cutoff probability that we got was 0.14. So for 0.14 probability, we again drew the confusion matrix, and this is the prediction we got from the model. So 85 bad credits were predicted as bad credit out of 91. So that is a pretty good accuracy by the model. So this was it. Thank you for listening to this binary logistic regression session. The next session will be on gain and lift chart, and also we'll be introducing the decision tree. Now, before attending the next session, we want you to install the graph-based a software based on the OS version, and also install the pi.plus. So thank you. This was it for this session.
That means we are done?
Yeah. Hello, sir.
Yeah. We are done, right? Can you hear me?
Yeah, recording is still on.
Yeah, thank you. So thank you for the linear regression and classification. Sorry, not linear, the the logistic regression and the classification you completed today. A little bit not sure about the recording, we'll check. But in between, there are some losses, but you seem to have continued very well. It says recorded, so we will release it if it is recorded properly.
Yeah.
And thank you for that summary of the binary logistic and all your German credit card which you presented, as well as the significance of the various measures which you adopted, especially Jordan's, and the area under the curve and the region over the curve, or what is the ROC AUC formulas and other things. Thank you, and we look forward to your next session. In the next, that is on the Wednesday. Thank you very much. Have a great day.
Yeah.
Bye. I will, what do you call that? Can you remove the recording? Stop the recording?